welcome back, guys. This time we're going to start our unit on the stars. Now, if I go ahead and move my head, you should see this wonderful galaxy behind me. Well, guys, we're going to talk about all the stars that are in that galaxy. Now, we're going to start with our sun. So now, quick, guys, what's our closest star? And you sit there pondering for a few minutes, and you're amazed how many people forget to say, well, gee, it's our sun. Yes, our sun is a star. It is not like the planets that we've talked about within the solar system. So what does that mean to be talking about a, quote, star? Well, let's talk about our sun. So let's talk about our sun. Obviously, guys, it's the center of our solar system. It's, at least for us, the most important thing out there, and it's certainly our nearest star, which actually a lot of people tend to forget. I think it's something else there. Well, this is a picture. I know it's not a picture of the sun, but I thought this picture was kind of cool because it reminds you of the fact that the reason that we have, flowers out there, everything else is basically because of our sun. And it, as I've said, provides that energy that we need to survive. But the other thing, even though it's 93 million miles away, it's what drives the Earth's climate and the weather. It's brighter than about 85% of the stellar population in our galaxy. So, guys, we're not that average star out there, But there are certainly stars that are a lot bigger than we are, and there's certainly stars that are a whole lot smaller than we are. We know that our sun is about 4.5 billion years old, and that makes it a third-generation star. And the way that they can determine that is, remember, we talked about the fact that at the beginning of our universe, we had nothing more than hydrogen and helium out there. Well, we see a lot of the other elements within our sun, and the only way that those other elements can get made is if you have a star that goes through its evolutionary sequence, goes through a supernova, and makes then these other elements, these heavier elements within the explosions as they go through their evolutionary sequence. And guys, for our purposes, heavier elements are basically anything that's heavier than helium. And so we know, based on the abundance of these elements that we have in our sun, that it's about a third-generation star. This kind of reminds you, if we look at our galaxy out there, that you see the core of our galaxy, and we're, just about a fourth of the way out. And when we look out in the summer and we look out in the winter, we are seeing two different parts of then our spiral arms. Our sun has a diameter of about 865,000 miles. Do I expect you to remember that number? No. But what I do expect you to remember is that I could then basically take about 110 Earths and line them up across the diameter of the sun. And as you probably already figured, that the sun then contains about 99.9% the mass of the solar system. So everything else then is the planets and all that kind of stuff. But our sun is basically the center and the most massive. It has an average density of about 1.4 times 10 to the third kilograms per meter cubed. Water has a density of about 1 times 10 to the third, or 1,000 kilograms per meter cubed. And then our Earth has a density of about 5.5, kilograms per centimeter cubed. It's about 5,500 kilograms per meter cubed. So you can see what that density is approaching, and we'll come back to that in the next section that we talk about, and talk about the density as an average, and then what's going on within the core of our sun. We know that our sun rotates once about every 28 days. And because it's not rotating as a solid body, at least not the outer parts of it, then the equator will rotate faster than what the poles do, so therefore the poles are going a little bit slower. We do think once you get down underneath that outer envelope of the sun, then it probably does more rotate as a solid body once you get down by that convection current. And like I said, that's about a fourth of the way down. We call it a yellow star, and that's because the majority of its output is in that yellow-green portion. Remember, guys, we see the way we do because we evolved under our sun, and so we see then best in the visible part and then in that yellow-green part of the visible spectrum. You can see that corresponds to a surface temperature of about 5,778 K. If you want to go ahead and round that off to about 5,800 K, that's fine. Remember, K is a Kelvin. I also you can see, put the temperatures down in terms of Celsius and Fahrenheit, probably the ones that you're a little bit more familiar with. But in terms of the scientific field, you tend to always use a Kelvin. Now, I want you to realize, though, even though the majority of that energy is put off in the visible part of the spectrum, our sun gives off the whole range of that electromagnetic spectrum, from gamma rays all the way down to radio waves. If I look at it outside the Earth's atmosphere, then our sun is going to appear very white. When we look at it here on the Earth, it looks a little bit more yellow, and that's because our atmosphere is going to go ahead and scatter out the really short wavelengths of light, which means that's of violets and some of the blues. And so we see basically an average of the energy that's left. Now, the one thing I would encourage you, if you have a full moon during the time that we're doing this, actually any moon works well, but full moon I know rises when the sun sets, then as that moon is coming up, you're going to see a really orangish red moon. And then as you observe that and the moon comes up even further, it will eventually go ahead and turn white. And the reason you're getting that really red color, because it's, again, going through a lot more atmosphere, and that atmosphere is scattering then the really top part of the spectrum all the way down to the greens, and so you're only getting that lower part of the spectrum. And it tends to show up really well when it's a full moon. Now, this is a picture of the Earth looking at, again, that atmosphere as you look then out over the Earth. And so we're looking through that atmosphere, and that's, again, why our sun appears yellow instead of white. This is what the sun looks like then if you look at it outside the Earth's atmosphere. Now, guys, you also know that those spikes in there are really not there. That's just because it had to be overexposed, and you're seeing that effect there. Our sun really doesn't have spikes on it. Now, I just like this picture. Remember I said it had that really nice yellow color on the Earth? I thought that was kind of a nice, cool picture of looking at the sun as it's coming through then the trees, and you kind of get that diffused light. Now, this picture is a picture of the sun, but I think it's a very different picture than what you've probably seen before. And this is certainly going through a very large amount of atmosphere, which is why you see that kind of reddish pink color. But then I also want you to look at the very top of the sun. That's not an optical illusion. It really is green. This is what's called a green flash. And as the sun sets, it is setting through a lot of atmosphere, and so that atmosphere then goes ahead and refracts the light that is going through that atmosphere. And so we actually are seeing the spectrum of the sunset. But because it's setting so fast, you still see it basically as one sun. And we will at times see a blue flash, but it occurs much faster. So here you can see the green flash, and by the time you look at it and blink your eyes, it's already gone. Now, we study our sun because of the information it's going to tell us about the characteristics, the behavior, and the evolution that it goes through. Because our sun is out there, and as I've said before, we're here because of our sun. Our sun provides all that energy. If something happened to our sun, we're going to be in trouble. So we want to take care of that sun. I really like this picture as well. See that sun there. So if we look at the northern hemisphere, and we've talked about this from the last unit, you know that the sun reaches its highest point in the sky, at least for us, in June, and that's what we call the summer solstice. It's going to reach the lowest point in the sky in December, which is our winter solstice. Remember that for the southern hemisphere, guys, when it's our first day of summer, it's their first day of winter. When it's our first day of winter, it's their first day of summer. Now, if you remember when we talked about seasons, then I have, for the summer, I have our axis in the northern hemisphere. The direction of that axis is pointed toward the sun, and so we're getting more of the direct rays of the sun, which means that when we're getting more direct rays of the sun, the Arctic then has 6 months of essentially day, and the Antarctic will have 6 months of night. And then, of course, then we'll switch it. So this is then a picture of the sun throughout a period of a year. And you can see at that very highest point, that's when we're going to have our nice summer solstice. And the sun is going to reach the highest point. It's going to be in the sky, and we'll have the longest days and the shorter nights. Then you can see that, indeed, that goes ahead and crosses at a particular point there. That's where we hit our equinoxes, which we have equal days and equal nights. And then you can see that it's going to actually, at the lowest point, be behind that hill or a mountain. And that's when we're going to have our winter solstice, in which case we're going to have the shortest day and the longest night. Now, if I then compare that with this picture, this is a picture of the land of the midnight sun. And this is a picture of the sun over a year as well. But we're looking at it from the Arctic, or you could also see the same kind of view down to the Antarctic. And so during 6 months, we are in continual daylight, and then we're in 6 months of continual darkness. And yeah, you will have some twilights in there, and you can see that path that sun takes. So now let's go back and talk a little bit more about the sun and exactly how the energy is produced in the sun. Now guys, on Blackboard, if you haven't already went ahead and copied it, I want you to stop right now. I want you to go to Blackboard and pull off the notes for this section, because I think you're going to find that they're very helpful, because we're going to go over some reactions, and they can be kind of confusing. But if you already have them laid out in front of you, where you're just following what I say and you're looking at the notes that are in front of you with all those reactions already written down, I think you're going to find it's going to help. So guys, if you haven't copied that off, do so now and then come back. Okay guys, so we know that the sun shines by emitting its own energy. You know, if I look at the moon shines by reflected sunlight. The earth shines because of the fact that the sun hits it and it's going to reflect that light back. Well, a star, on the other hand, is actually making its own light. So where does it get the energy to go ahead and do that? And we know from a great deal of study that the way that you can account for the types of energy we see given off by stars are the fact that they are undergoing thermonuclear reactions within the core. And so if I think about what a star is, our sun included, it's an enormous ball of extremely hot gases shining under its own power. And that will describe a lot of those stars out there. And so we'll just talk about how then that star is changing as it goes through its evolutionary sequence. So another picture of the star, in this case our sun. And originally, when ancient people were trying to decide exactly how that sun was shining, they were thinking maybe somebody was up there, producing lots of wood where you were burning inside the core of that sun. And we know that that's not nearly enough. There's a tremendous amount of energy that sun has given off, considering its size and considering it's been around for almost 5 billion years, and we know it's going to be around for another 5 billion years. And we also know that looking at the sun, and from what we've been able to determine, that the sun contains the same atoms as what we do here on the Earth, but certainly not in the same abundance. The Earth, the planets, tend to be very different than everything else we see out there. Most of the rest of the universe contains hydrogen or helium, and then a little bit of everything else. Here on the Earth, we contain a lot more of everything with a little bit of hydrogen and helium. And so the stars formed of mostly hydrogen, some helium, and then a little bit of everything else. And as I said earlier, guys, everything else includes everything above helium. Within a star, these things are found mostly as atoms and ions. The fact that you have these molecules that simply cannot stay around because of tremendous temperatures and pressures. And even that within the atoms, a lot of times what we're going to see is the atoms have been stripped off of their electrons, and so you have just the atomic nuclei left as opposed to what we really consider a neutral atom. Now, one of the first people to really look at what the abundance of these elements on the sun were was a lady by the name of Cecilia Payne. And she was looking at this in 1925, and unfortunately, ladies, when she was doing her work, because she was a female, she was not allowed to go ahead and actually teach at Harvard, nor was she really allowed to attend classes, things like that, and certainly not to go ahead and get her PhD there. That has changed a great deal from 1925, and she certainly did end up teaching there in the latter part of her life. But she was an excellent looking at the abundance of those elements within the sun by looking at the solar spectrum, and later on I will have a picture of that spectrum, and we'll talk about those absorption lines that she was looking at to determine the chemical abundance. But when she did, she didn't believe it. The data was there, But it was really hard to understand because most people assumed that the star was made out of nothing more than hydrogen and helium. And so if you go back and look at some of her early writings, while she was doing that work, she said the enormous abundance derived for these elements in the stellar atmosphere is almost certainly not real. Well, it certainly was. It just took the ideas and the model of what was going on with the sun or with the star to catch up with what her observations already showed. And this is certainly Cecilia. This is in 1923. And if you go read about her life, I think you'll find that it's very interesting, especially a lot of the early women astronomers, and there actually were a number out there, that brought along then their techniques and what they were finding out, and finally became then accepted to work with all the rest of the gentlemen out there. So let's talk about the parts of the sun. I have a core. I have a radiative zone or radiation zone, however you want to refer to it. I have a convective zone or a convection zone, photosphere, chromosphere, corona, and the heliosphere. Now, each one of these are very distinct layers within the sun itself. And if we look at the sun, just like we looked at the Earth, we'll compare all the other suns out there, all the other stars out there, with our sun, just like we compared all the planets out there with what was going on with the Earth. Now, this kind of just shows a schematic of what the sun and the core of the sun looks like. So take this big, enormous ball of gases out there and just take a chunk out of it. And at the very center, I'm going to see that core. And that core is where we're going to find that these thermonuclear reactions are occurring. Then above that, you get a radiation zone where you just have an energy that is outflowing. Above that, we get a convection zone where we have big convection currents set up. And then above that, you have that outer envelope of the star, of our sun, and you have a photosphere, a chromosphere, and a corona. The photosphere, think of that as where you can no longer see into or through the outer clouds. It's kind of that opaque layer of the sun, and so we call that the surface, even though, guys, you need to realize it's certainly not a solid surface. You can't go out there and land on the sun. You'll just go zipping through, and at that point you're going to be burned up anyway. So, you don't want to try that. Then above the photosphere is this coronosphere, which we very rarely get to see unless we're in a solar eclipse. And then above the chromosphere, you have the corona. The only time we can really see the corona is during a solar eclipse. And remember I said that the surface temperature of the sun was about 5,800 K? Again, no solid surface, but it's right around that photosphere. We're going to find that that's not true in the temperatures within the corona. Much, much, much higher, approaching millions of degrees. So, we're going from 5,800 K to, these incredibly high temperatures. And we're going to find we're going to do that in a very short period of time, corresponding to a very short distance then that energy travels through. So what's going on there? As you would expect, guys, the density of the sun is going to be the highest in the center, and then for the most part, they're going to decrease as you move outward. And again, for the most part, same way with the temperature. The highest temperatures and higher pressures are going to be inside that core, and then as you move out, those temperatures are going to go ahead for the most part and decrease. And boy, by the time we are in the core, there is not going to be any solids or liquids, and that's pretty well true anyway for everything within our sun and the other stars. You're not going to have any kind of solids or liquids. The energies are just too great in there. They're moving too fast, and nothing is going to survive as a solid or a liquid. Not hardly going to survive too much as a gas until we get to that outer envelope. Mostly everything's going to be subatomic particles. Now, we obviously can't observe the sun directly. I mean, we can't even observe the Earth directly. But the same way that we indirectly observe the Earth's core, we're going to do the same thing in indirectly observing the sun's core. We can't get down there. You can't reach out and touch that. But we can talk about something called seismology. Okay, now we think about using seismology here on the Earth, then I'm looking at, let's say, an earthquake wave, and I can track how that earthquake wave is traveling through the Earth. If I put detector stations, seismic stations all around the Earth, and I have a really big earthquake that goes off, I can determine how long that wave took to get to the other detectors, things like that. And that tells me something then about what's going on within the interior of the star, within the interior of the Earth. So we're going to apply that same kind of thing to the sun. Only we call it helioseismology, and you're using acoustic pressure or those waves or those pulses that you can use to model the interior part of the sun. And on Blackboard, guys, I've got a website that I'm going to simply send you to, and I want you to listen to those waves on the sun. It gives you kind of a weird feeling. So the sun, we know, pulsates just like the Earth pulsates. It's going to expand and contract, and a lot of it's because of the turbulence that you see in those big convection zones, because these things are bringing material up to the top, then it cools off and it sinks back down. Well, we can measure those pulses that are coming up, those convection currents, and how quickly they dissipate using the Doppler effect or the Doppler shift. Remember, the Doppler effect is just that apparent change in frequency due to the motion of the observer or the source or both. And so what happens is we are looking at the Doppler shift of the solar absorption lines. I know that may not mean anything to you yet, but we'll show you what the absorption lines look like here in just a minute. So as that sun's velocity is changing, is it coming toward me? Is it going away from me? Exactly what's happening. And we can look at those changes, and they occur, about 5 minutes, and a size range of about 2,500 to about 9,400 miles. But knowing that and being able to measure that and being able to then build a model based on how to reproduce that data, that information that we collected, gives us a way then of understanding the temperatures and the densities and the compositions of all the layers that are in our sun. So this is nothing more than some of the images of the data that has been collected. And you can see something then about the sun based on those waves or those pressures, and you get these pulsations. And like I said, the wavelength that the URL that I'm going to send you to has converted these pulses into acoustical recordings, sound, so you can go ahead and listen to, and you listen to those pulses that the sun is sending out. And again, where those are and what they sound like will give us a feel for what's going on in the interior part of the sun. This is that website, guys. You don't need to worry about taking this down, because I also have that website on Blackboard. And I've asked you a few questions over this once you get to Blackboard and have a chance to listen to those recordings. Now, if we think about what the core of the sun is like, it has a density of about 150,000 kilometers per meter cubed. So that's about 150 times the density of water. And look at that temperature. We have a surface temperature of 5,800 K. We have a core temperature of about 13.6 million degrees. Huge difference between then the core temperatures and the surface. And that energy is basically produced by thermonuclear reactions, and those thermonuclear reactions are going to convert hydrogen into helium. So, what kind of reactions are we talking about? You're probably already familiar with both of them. We can talk about a fusion reaction or a fission reaction. And the one we're going to deal with more is going to be a fusion reaction. So we're taking small nuclei and we are smashing them into other small nuclei, and we're building larger nuclei. If I think about the nuclear reactors here on the Earth, then that's fission. So you're taking these really large atomic nuclei and you're breaking them apart. We're fusing, not breaking. Everybody knows this equation. I don't care who you ask out on the street, they probably know this equation. Most people don't have a clue what it really stands for. And the other thing is most people, when they talk about this equation, leave that little triangle part of the equation out. This is nothing more than a statement of the law of conservation of matter and energy. And it says that matter and energy can neither be created nor destroyed. They can only change form. E stands for energy. That little triangle stands for the change in. So that tells me to get some energy, I've got to have some kind of mass change. And that mass change then gets multiplied by the speed of light squared, and that gives me an equivalent amount of energy. This is the most effective way to get energy out. You simply take that mass, you convert it into energy. Remember, guys, the speed of light is 3 times 10 to the 8th meters per second, or 186,000 miles per second. So that's a really big number, and when I square that, even if I have a really small mass, I'm going to get out some good amounts of energy. Now, we're going to go through a couple of these reactions, guys, and that's why I want that little sheet of paper in front of you so that you can concentrate on the information, not trying to get this information down. There are some terms that you need to know, and one of them is called the atomic number. Now, you also, when you printed that information off, you should have also printed off a periodic table. So I want you to have that out. I want you to have those reactions out. Now, when you look at that periodic table, every one of those elements has a unique number, such as hydrogen is 1, helium is 2, lithium is 3, and so on. Well, that number right there is the atomic number, and that corresponds to the number of protons. The atomic mass number, on the other hand, is the number of protons plus neutrons. And so that is a nice whole number. And it just then is talking about the number of protons plus neutrons. And then we have an isotope, which is the same number of protons, but different number of neutrons. And so basically an isotope is, like to be talking about hydrogen. There are 2 isotopes of hydrogen. There's regular hydrogen. There's deuterium, which has 1 proton and 1 neutron. And there's tritium, which has 1 proton and 2 neutrons. So again, all it's going to do is give you a difference in terms of the mass, but chemically it is not going to behave any different in any kind of reaction. It's only going to behave differently with those thermonuclear reactions, the reactions that occur within the core of that atom. Then we have something called the binding energy. And that binding energy is the energy required to go ahead and completely separate those particles that are making up the nucleus. And when that energy then is released, we see it then as energy that comes off, but we know that it was originally the energy that was required to hold the nucleus together. Which means, guys, I'm going to look at a difference in mass between what happens when I have particles that are held together within a nucleus and particles that are exactly the same types of particles. They are just free, moving off by themselves, no longer confined within the nucleus. So we've got that mass-energy conversion right there. Okay, so there's a certain amount of binding energy required that's going to go ahead and be the energy that's given off when you separate that nucleus. So let's talk about these reactions. Now, you've got listed there some proton numbers, some neutron numbers, some atomic mass unit numbers, things like that. What I want to do is I want to look at the mass of a proton and a neutron when they're separated, so they're out there freely roaming around, not necessarily together, they're roaming around. And then I want to look at the mass of a proton and neutron when they're combined within a nucleus. And I want to see if there's any difference between that mass. Now, the other thing, guys, you see there's a mass unit called an atomic mass unit. And atomic mass unit is just a unit that's used to simplify numbers when I talk about incredibly small numbers. We're talking about masses on the order of 10 to the, very, 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 very tiny grams or kilograms. Okay? So keep in mind, we just came up with another unit to be able to deal with that. And we call that an atomic mass unit, and that has an equivalent mass when we talk about the mass in kilograms. Notice that the proton has an atomic mass unit of 1.007825, and I do need to go ahead and carry those things out to those decimal points. The mass of a neutron has a mass of 1.008665 atomic mass units. And if I add those two together, then I'm going to get 2.016490 atomic mass units. Now, guys, go look at the mass of that neutron. Okay? That neutron is just a tiny bit larger than the mass of a proton. Okay? And so that's because you can kind of think of a neutron as a neutral particle, but if I take a proton and I put it together with an electron, proton being positive, electrons being negative, then I'm going to end up with a neutron. Now, that works well thinking about a proton plus an electron goes ahead and gives me a neutral particle. In reality, guys, we know that those protons and neutrons are made up of things called quarks, and depending on how those quarks rearrange themselves, you'll get the properties of a proton or a neutron or other kinds of subatomic particles that we have out there. We're not going to get to that level of quarks until we come back to the very last chapter that we talk about, which will be the Big Bang that actually started our universe. And then we'll come back and talk about those quarks. So now, individually, they have a mass of 2.016490 atomic mass units. Now when I look at them in terms of the mass of that deuterium, deuterium is hydrogen, which means it has one proton, and one neutron combined within a nucleus. Then I see that that has a mass of 2.014102 atomic mass units. Now guys, notice that those two numbers do not equal the same. There is a difference in mass between 2.016490 and 2.014102. So something happened. I changed mass in there. I increased my mass just by separating those two particles outside of the nucleus. Okay? And my difference, when I go ahead and subtract that, is 0.002388 atomic mass units. Aren't you glad you're not having to write this down? Very nice to have that laid out in front of you. So what does that really mean? If I have 0.002388 atomic mass units, how much energy am I getting out of that? How much energy is that difference in mass associated with? Excuse me. So I'm going to do some conversions here. I know one atomic mass unit is basically 1.66 times 10 to the minus 27 kilograms. Okay, guys, that's a standard. That's what your atomic mass unit was set up on. And 1.67 times 10 to the minus 27 kilogram is about the mass of a proton or a neutron. Okay. Now, I'm going to take that 0.002388 atomic mass units, and I'm going to multiply that then by my conversion factor of that 1.66 times 10 to the minus 27 kilograms per one atomic mass unit, and I'm going to get a mass of 3.96 times 10 to the minus 30th kilograms. And yes, guys, that's a really, really, really small amount of mass. Could you ever see that? Absolutely not, because we're talking about masses that are on the atomic, actually on the nuclear stage there. Very, very tiny. But if I then go ahead and look at my energy, energy is equal to the change in mass times the speed of light squared. So you can see my calculations right there. And so I come out with an energy of 3.56 times 10 to the minus 13 joules. And I know you're saying, but hey, that's a really small number as well. Well, yes, it is, guys. It's a really small number. But notice that that really small amount of energy came out from a really even much, much, much smaller amount of mass. So how does a thermonuclear reaction, how does a reaction that we've just looked at compare with burning, let's say, coal or something else like that? So guys, I want you to kind of keep that number in mind. And let's look at the energy given off by 1 kilogram of hydrogen. So in other words, I take 1,000 grams, and 1 kilogram is equivalent to a weight of about 2.2 pounds. So think about what 2.2 pounds is. And I'm going to take that weight of hydrogen, and I do those calculations, and that gives me an equivalent energy of 6.4 times 10 to the 14th joules. That's, guys, a whole lot of energy. I want to compare that with what happens if I just burn a ton of coal. Remember, a ton's about 2,000 pounds. If I burn a ton of coal, I'm only going to get off 3.2 times 10 to the 10th joules. That's a factor of 10 to the 4th smaller than what I'm going to give off if I just go ahead and convert 2.2 pounds of hydrogen into energy. And so when you look at it that way, guys, it's a huge difference. Okay, 2.2 pounds of hydrogen versus 2,000 pounds of coal. It'd be really great if we could get a nice fusion reaction to occur here on Earth, and we could power our homes or our buildings or our cars with fusion reactions. It's great. I mean, it's a tremendous amount of energy out there. Hopefully you recognize this. This is a picture of Star Trek Enterprise. And so why do I have the Enterprise on there? Well, guys, if you know anything about Star Trek and how the Enterprise runs, is you know it runs off of a matter-antimatter engine. Well, that's an excellent type of an engine. You are completely converting matter into energy, because what happens is you have that matter, it hits its anti-particle, and you get complete annihilation. So you get that change in matter, change in mass, then, which gives you the energy. And so we know there are particles out there that are called antiparticles, and a particle and its antiparticle are exactly alike with the exception of charge. And the example that I gave you is an electron and a positron. An electron is a negatively charged particle. A positron is a positively charged particle. They are exactly alike. They are exactly the same size. Every bit of those characteristics, except that positron carries a positive charge. An electron then carries that negative charge. Now, particles like neutrons, which are neutral, will not have antiparticles, because you can't have the anti of something that's not charged. You know, the anti of 0 is still 0. Okay. And then I want you to know something about a neutrino. These are little bitty small, and I do mean really, really, really small, essentially massless particles, hence that's why they're small, with no charge, and they're going to help to carry away the energy when we start looking at these reactions. Now, neutrinos were kind of proposed back in 1933, but because they have such a huge velocity, you know, there is no charge, they're essentially no mass, it's really difficult to get these little neutrinos to go ahead and react with anything. And so we did not find the first one until 1956, and we're still not really finding them the way that we think we should. We're certainly getting better, okay? But they simply are hard to find because they do not go ahead and react very well. And again, I've got some questions on Blackboard. I want to take you and have you look at a neutrino detector and see how it's going ahead and detecting those neutrinos. Now, we know about 3% of the total energy generated by the sun is kicked out from the core and is carried away by the neutrinos. And those things go directly out. They do not take any time at all to kind of work their way through the radiation zone, convection zone, things like that. They head right out. Okay. Now, we think that there are about, according to our best models, about 3.5 times 10 to the 16th neutrinos that are passing through each square meter of the Earth every second. Guys, look at that. 3.5 times 10 to the 16th neutrinos. We're not detecting nearly that many. And it's just because they are moving so fast and they don't react. They're very hard to find. But they're zipping through us all the time. We're never going to know it, and it's never going to bother us. Now, the extremely high temperatures in the core are going to cause these protons to move extremely fast, and they're going to collide. And eventually, they're going to get enough energy that when they smash together, they're going to go ahead and stick. And that's going to start something called the proton-proton chain, and that's the chain then that goes ahead and powers the sun. So in the core, you have these incredibly high temperatures and incredibly high densities. You have to get the densities high enough to get the ions in there, or the nuclei in there, nucleus is in there, and you have to get them moving fast enough and have enough of them that when they smash together, they actually go ahead and stick. So this is a proton-proton chain. Okay, so I've got now a chain means that, okay, it starts at one end and keeps going. Okay, and so this is going to power basically the sun for about 10 billion years. Okay, so this has got to be pretty effective in producing energy. And it just gets used over and over and over and over and over again. So let's say I look at step number 1. Step number 1 starts with regular hydrogen. Now, any other time you would see that hydrogen and those two little numbers, you would generally always see them on the left side. So it would be a 1 over a 1. I can't seem to make my computer do that, guys. So I have to write it as 1 on one side and 1 on the other. But keep in mind those numbers should both be more correctly written on the same side. Irregardless, let's talk about what those things mean. Okay, the one in the upper left stands for the atomic mass number. So that's a number of protons plus neutrons. The number in the lower right stands for the number of protons. So if I'm talking about hydrogen, I'm literally talking about a free proton right here. And then I go ahead and have another free proton in there, and I smash these two together. And when I do that, then I end up forming, again, hydrogen, but this time my hydrogen has one neutron. So I'm forming deuterium. In the process of forming deuterium, I have two particles that are given off. The little e to the plus is my positron, so that's a positive electron that comes from the nucleus. And then that little v is my neutrino. So that energy given off by that neutrino then gets carried away. It goes zipping through the sun, heads on out through the solar system. Then my second step, I take that deuterium, okay, which is heavy hydrogen, one neutron, one proton. I add it to another proton, and I form helium. Now, it's not the normal helium that's a real stable helium. This is called helium-3. And like I said, it's not stable at all. And I have 3 mass particles. Of those 3 mass particles, 2 of them are protons, so that means one of them has to be a neutron. And like I said, that's going to be really unstable. The other particle that is given off is not a particle itself. It's part of the electromagnetic radiation. It's actually a gamma ray. And that gamma ray then will slowly make its way from the core out to the edges of the sun and then be given off as energy. Now, I've got to have 2 of the 2H of those deuterium ions. So I have to do step number 1 twice. So now I get my 2, I can go ahead and add it to my proton. I'm going to form another helium-3 because then in step 3, I need both those helium-3s. So that means then I have more neutrinos coming out of there because of step 1. Then I go to step 3. I now take those 2 helium-3s, smash them together, and I form helium-4. Helium-4 is extremely stable. It's also called an alpha particle. It has 2 protons and 2 neutrons. And so that combination of 2 protons and 2 neutrons is extremely stable. And notice, guys, what's given off. I have 2 protons that are given off, 2 of those 1,1 hydrogens. Well, that's good because I can use those 2 free hydrogens to start my chain over again. If I smash those 2 hydrogens together, I produce deuterium. In the process, I give off a positron and a neutrino. Smash them together with a deuterium and a proton, get helium. Smash my heliums together, get helium-4 plus 2 more hydrogens that are going to start that reaction again. So like I said, that hydrogen gets recycled over and over and over again, which is helping to then go ahead and power the sun. Now, just to give you some idea of what our sun is doing, it's converting 4.3, that's a million tons, guys. 4.3 times 10 to the 6th tons of matter into energy each second. And so that's equivalent to about 600 million tons of hydrogen being converted into helium every second. Guys, that's a lot of energy, but that's okay because our sun is a really big star and it needs that energy to go ahead and keep burning. Now, this is a picture of the sun. And I want you to look at that and you see that kind of seething core or surface that's boiling. I want you to think about a surface of boiling water, okay, and then put the motion of that boiling water onto that sun, and that's what the sun itself is going to be like. Now, that's what the outer layer of our sun looks like when we're looking down right on that surface, and that's powered by those reactions. So for today, I want to go ahead and stop here, kind of give you a chance to mull over those reactions and kind of see what's going on. The last page that you have in there is an example of a problem I would like for you to work that deals with those conversions and looking at what happens if I give you a certain mass difference and allowing you to figure out the energy that's associated with that. So please try that before the next time we're together. With that, I'll see you next time.